Uranium, a naturally radioactive element, is found dispersed throughout the Earth's crust. It's a fundamental building block for nuclear energy, present in varying concentrations in different geological formations around the world. However, not all uranium is directly usable for generating nuclear energy in power plants. The key lies in the specific isotopes present within a uranium sample. The vast majority of naturally occurring uranium, over 99%, is the isotope U-238. This isotope is relatively stable and on its own not very efficient for sustaining a nuclear reaction for power generation. The isotope that truly matters is U-235. It's relatively rare, making up less than 1% of natural uranium, but it's absolutely crucial because it's capable of sustaining a nuclear chain reaction, the very heart of nuclear power. When uranium is mined from the Earth, it contains only a small fraction, about 0.7%, of the U-235 isotope. The remaining bulk, over 99%, is composed mostly of U-238. To make uranium suitable for use in most nuclear power reactors, we need to increase the concentration of U-235 to somewhere between 3 and 5%. This process is called enrichment, and the resulting product is known as low-enriched uranium, or LEU for short. Enrichment effectively increases the proportion of the U-235 isotope, making nuclear chain reactions not only possible but also far more efficient and sustainable for continuous power generation. However, if the enrichment process continues to push the U-235 concentration significantly higher, specifically above 90%, you end up with highly enriched uranium, or HEU, which is the type of material required for the creation of nuclear weapons. It's important to realize that the very same enrichment technology can be used to produce fuel for nuclear power plants, or, concerningly, to create material for nuclear bombs. The critical difference lies solely in the final concentration percentage of U-235 achieved. This dual-use nature is precisely why uranium enrichment is subject to such stringent controls and monitoring worldwide. The enrichment process itself is essentially a form of atomic-scale sorting, a delicate and complex undertaking. It involves physically separating the relatively rare and valuable U-235 isotope from the far more abundant U-238. Without the process of enrichment, nuclear reactors simply wouldn't have a sufficient amount of fissile material to initiate and sustain a chain reaction, and therefore could not operate. The fundamental physics of nuclear fission dictates that a certain minimum concentration of U-235 is absolutely necessary to achieve and maintain a self-sustaining chain reaction. Therefore, enrichment stands as the critical and indispensable step that unlocks the immense energy potential contained within uranium. It's the transformative process that converts a relatively common mineral found in the Earth into a powerful and concentrated source of energy. This crucial step represents both a remarkable technical achievement and a significant global security concern, demanding careful oversight. Therefore, gaining a solid understanding of uranium enrichment is absolutely key to comprehending both the benefits and the potential risks associated with nuclear power. Uranium's journey starts, not in a reactor, but far beneath the surface of the Earth. Deep underground, in the heart of the Earth's crust, where miners extract ore that, to the untrained eye, looks like ordinary rock. But within this seemingly mundane stone lies the potential for immense power. The ore is then subjected to a rigorous process, first crushed and milled into a fine powder, ensuring maximum surface area for the next stage. This powder is then chemically treated in large industrial facilities, carefully managed to dissolve out the uranium from the unwanted materials. This crucial process, called leaching, separates the valuable uranium from the rest of the ore. The result is a concentrated yellow powder known as yellowcake, chemically identified as uranium oxide or U3O8. At this stage, yellowcake still has the natural ratio of isotopes. Only a small fraction, about 0.7%, is the fissile isotope U-235. To unlock the full potential of nuclear energy, we need to separate the U-235 from the more abundant U-238. To achieve this separation, we need the uranium in a gaseous form, a critical step in the enrichment process. Therefore, the yellowcake is converted into uranium hexafluoride, or UF6, which conveniently becomes a gas at relatively low temperatures, making it easier to handle and process. In this gaseous state, the incredibly tiny mass difference between U-235 and U-238 can be exploited for enrichment, a process that requires extreme precision. Each UF6 molecule contains either a U-235 or U-238 atom, dictating its mass and behavior. And this minute difference in mass is the key to the entire separation process. This conversion from a solid rock to a processable gas is a major industrial undertaking requiring both extreme precision and stringent safety protocols at every step. Only as a gas can uranium be enriched, prepared for its ultimate purpose, sorted atom by atom, a testament to human ingenuity. This transformation sets the stage for the complex and energy-intensive enrichment process that follows. Indeed, every nuclear fuel cycle, regardless of reactor type, begins with these essential chemical transformations, laying the foundation for clean and reliable energy. With uranium hexafluoride gas ready, the next hurdle looms large. The core challenge is separating the slightly lighter, more fissile U-235 from the heavier, more abundant U-238. This difference in mass is the key to the entire process. The first method developed for large-scale enrichment was gaseous diffusion. UF6 gas is forced under pressure through barriers riddled with countless microscopic holes, selectively letting the lighter U-235 molecules slip through the porous membrane ever so slightly faster than their heavier counterparts. The difference in permeation rate is incredibly tiny, necessitating that the process be repeated tens of thousands of times in cascading stages within massive, sprawling plants. Gaseous diffusion represented a monumental engineering feat for its time, but it was also an extremely energy-intensive and ultimately an inefficient method. Today, advanced gas centrifuges have become the global standard for uranium enrichment. A centrifuge rapidly spins the UF6 gas at extremely high speeds. The resulting centrifugal force causes the heavier U-238 to migrate towards the outer walls, while the lighter U-235 isotope remains concentrated closer to the center of the rotating cylinder. This physical separation is significantly more efficient compared to gaseous diffusion. Furthermore, modern centrifuge designs often incorporate temperature gradients within the centrifuge to further enhance the isotopic separation process. While each individual centrifuge provides only a small degree of enrichment, they collectively consume only a small fraction of the electrical energy required by older diffusion plants. This dramatic reduction in energy consumption is the primary reason why centrifuges have largely replaced gaseous diffusion technology worldwide. The global transition to centrifuge technology has made uranium enrichment significantly faster, substantially cheaper, and ultimately more accessible to a wider range of nations. This increased efficiency has profound implications for both nuclear energy production and global security concerns. A single centrifuge can't enrich uranium enough for reactor fuel. The separation per pass is minimal. Enrichment plants connect thousands of centrifuges in a series called a cascade. Each stage slightly increases U-235 concentration, passing enriched gas to the next stage. Depleted streams are recycled to maximize U-235 extraction. The final product, low-enriched uranium, is drawn from the top. Depleted uranium, mostly U-238, is removed from the bottom. The cascade size and configuration determine the enrichment level and output. More stages mean higher enrichment, enough for weapons if pushed far enough. That's why cascade design is so sensitive and closely monitored. Reconfiguring a plant can shift it from peaceful to military use. The complexity of these systems is both a technical and security challenge. Enrichment plants are marvels of engineering and global oversight. Scientists are exploring laser enrichment as a next-generation technology. Instead of relying on mass differences, lasers target the unique light absorption of U-235 atoms. In AVLAS, uranium is vaporized and hit with lasers tuned to excite only U-235, which is then ionized and separated with magnets. This could, in theory, enrich uranium in a single step, making facilities smaller and more energy efficient. SILEX, another method, uses lasers on uranium hexafluoride gas, fitting into existing infrastructure. Laser enrichment is still experimental and highly classified. Its efficiency could revolutionize enrichment, or make proliferation harder to detect. The technology's promise is matched by its risks. For now, centrifuges remain the global standard, but lasers could change the game. Once uranium is enriched, it's still in the form of corrosive UF6 gas, not suitable for reactors. The gas is converted into uranium dioxide powder, which is stable and heat-resistant. This powder is pressed into small ceramic pellets and baked at high temperatures to harden them. Each pellet packs enormous energy. comparable to a ton of coal. Pellets are stacked into long metal tubes, usually made of zirconium alloy, forming fuel rods. Fuel rods are bundled into assemblies, hundreds per reactor core. This structure safely contains the fuel and allows efficient heat transfer. The entire process is engineered for safety, durability, and performance. These fuel assemblies are the heart of every nuclear power plant. Uranium enrichment is a classic dual-use technology, fuel for power or material for bombs. The same centrifuges can make reactor fuel or weapons-grade uranium, depending on how they're run. That's why enrichment is one of the world's most closely monitored processes. The Non-Proliferation Treaty, NPT, and the International Atomic Energy Agency, IAEA, oversee global safeguards. IAEA inspectors visit facilities, install cameras, and track nuclear material to ensure it's not diverted. Despite these safeguards, proliferation risks remain. Secret facilities or treaty withdrawals are constant concerns. The spread of enrichment tech is tightly controlled, and international cooperation is vital. Balancing peaceful nuclear energy with global security is an ongoing challenge. Enrichment is not just technical, it's a huge economic and energy challenge. The effort is measured in separative work units, or SWUs, which quantify the work needed to separate U-235 from U-238. SWU prices have soared recently due to geopolitical shifts and supply chain disruptions. Russia has long dominated enrichment and conversion, but Western countries are now scrambling to build alternative capacity. The market is concentrated among a few players: Urenco, Orano, Rosatom, and China. This makes the supply chain vulnerable to shocks. Advanced reactors need HALEU fuel enriched to 520% U-235, but commercial supply is scarce with Russia as the main source. Expanding enrichment for HALEU is a top priority, but it will take years and major investment. Ensuring a stable, secure supply of enriched uranium is critical for the future of nuclear energy. The economics of enrichment shape the entire nuclear industry. Uranium enrichment is at the heart of the nuclear age, offering clean energy and posing profound risks. Nuclear power provides about 10% of the world's electricity, helping fight climate change. Advanced reactors and medical isotopes also depend on enriched uranium, but the same process can create material for nuclear weapons, demanding strict oversight. The IAEA and global treaties are essential for managing this double-edged technology. Enrichment is a triumph of science and engineering, but also a test of global responsibility. How we handle enrichment will shape our energy future and global security. The challenge: harnessing the atom's power for good while guarding against its dangers.